Hi, welcome back to Calculus. Today we're going to be doing integration using rectangles, otherwise known as Riemann sums. Now, first things first, what is integration anyway? Well, integration is defined as the cumulative area between two lines on a graph between two different x values. So in other words, if you either take two functions or a function and the x-axis and you draw two lines at two different x values, done very, very shoddily by me, right here, now we have a shape in which we can find the area of. And that's what we essentially are doing here. Throughout the entirety of this is the equation in which we're going to be using. Now, in order to break this down, this is the integral of x cubed minus 5x squared plus x plus 16 with a left bound of 0 and a right bound of 5. Or in other words, we're going to be finding the area between this and the x-axis between the x values of 0 and 5. Now, how this is normally done is by using something known as the antiderivative. Now, what is an antiderivative? You see, the antiderivative is the sister of the father of the derivative. That is a joke. That is not what it actually is. The antiderivative is taking the reverse of a derivative. If you take a derivative of something, which if you're watching this, you probably already know what it is, you go the other way. It's known as the antiderivative. Now, it's quite a lot more complicated than that, as you can see, but in general, that's what it is. In order to integrate using an antiderivative, you first take the antiderivative of the original equation. So x cubed minus 5x plus x plus 16 turns into this using witchcraft or whatever, and then subtract the result of 0 from the result of 5. What that basically means is that if you assume that this is f of x, you subtract f of 5 and f of 0 to get your answer, which in this case is 40.416 repeating. Now, we didn't always know what the antiderivative was. Newton only discovered this in like 1600s, 1700s. So the question is, what did people use before then? Well, they used something known as Riemann sums. So here you'll see that I have two exact copies of the above formula in which I had before. Now what we're going to be doing here is we're going to be taking a Riemann sum of this. Now what is a Riemann sum? Well, I'm glad you asked. A Riemann sum is drawing a whole bunch of rectangles all across a graph. Now, to ease calculations here, I'm going to be drawing these rectangles with a width of 1. The reason being is that later on we're going to be taking the area of every single one of these rectangles and we're going to be adding them together. That is essentially what a Riemann sum is, adding up the areas of all of these rectangles. If the width was not 1, then I couldn't just use the heights. So just for ease of simplicity, I'm going to be using a height of 1 and therefore 5 rectangles. So let's draw a whole bunch of rectangles. We're going to be drawing these rectangles with a right bound. That means that if I place a rectangle right here, then that will essentially be touching the graph on its right boundary. So there's a rectangle. Here's a rectangle. Here's a rectangle. Let's see here. Here's a rectangle. And all the way up here is a rectangle. Now, if I drew this correctly, which as you can see, I probably did not because that's 12 and that's 13. But in any case, if you drew this correctly, then you have a whole bunch of rectangles of an area of, pretending this is 12, 12, 6, 1, 4, and 21. So you take the areas of these and then just add them up. 12 plus 6 plus 1 plus 21 plus 4 equals 44, which is approximately the area of this entire line between those 2 points. Now, 44 is actually pretty close to 40.416 repeating. However, we can do slightly better than that. Or, to be more specific, we can do quite differently from that. On this left graph, we used right-bounded rectangles, so on this right graph, we shall use left-bounded rectangles. So let's do that. Draw a whole bunch of rectangles which touch the graph on the left. There's one, there. Goes a bit far, but that's not really of concern, and right there. Now we have our 5 rectangles again. This time it's 16 plus 12 plus 6 plus 1 plus 4. You'll notice that there's quite a few numbers in which happen to overlap between the two, 12, 6, 1, 4, 12, 6, 1, 4. The reason for that is that the right bound of this rectangle is going to be at the left bound of this rectangle. So you're going to have a whole bunch of repeating numbers. This is entirely normal. And once again, as with the right bound, we take all of the heights of these, since the width is 1, and we add them. 16 plus 12 plus 6 plus 1 plus 4 equals 39. Now we can take the average between these two in order to get a better picture of what exactly the area of between this function and the graph is. And if we take the average, it's 41.5. It's pretty close. And I'm sure that if I had actual singular unit grid lines instead of whatever the heck OneNote gave me, then I could draw it even better and get even closer to the actual target. But 41.5 is not that bad. So once again, as I so often say, if you can't do it with numbers, it's not worth our time. So let's do it with numbers. This is what we're doing, generalized into a mathematical formula in which does not actually require us to draw a whole bunch of lines on a graph every single time. B minus a over n multiplied by the summation of f of xi, where I starts at 1 and it goes all the way up to n. Now let me break this down for you a little bit. First things first, b minus a over n. b is the right bound, a is the left bound, and n is the number of rectangles. I wrote squares here, that doesn't matter. This here will give you the length of every single square, or not the length, more specifically, the width. The width of every single rectangle is going to be exactly the same. And that is once again given by the difference in left and right bounds over the number of squares. In our case, 5 minus 0 over 5 would be 5 over 5 equals 1, which was why I was able to use just the heights. However, if you want to add more rectangles, which increases the accuracy, then this number here will change. Now next we have the summation of f of xi. Believe it or not, before starting this unit of calculus, I had never seen this symbol here outside of that one time I tried to learn Greek. So what this essentially means, in the event that you don't know, is that you're taking f of x1, f of x2, and then you're just adding up the result of each and every single one of them. Now fxi, what you're doing here is you're doing x number 1, x number 2, x number 3, x number 4, x number 5. Each and every single one of these x's is whatever the bound is in which you are taking the measurements off of. So if you're taking right bound, then your first xi will be 1, then 2, then 3, then 4, then 5, because the function at those points happen to be equal to f of x at whatever the x was in which you were taking from. I hope that made a single shred of sense. And then finally, you're going from the index in which starts at 1, going all the way up to how many there are. You go from the first x, second, third, fourth, and oh look, there's 5, end of 5. So now that we've seen the general case, let's break down our own case. So in our case, 5 minus 0 over 5 multiplied by the summation of xi cubed minus 5xi squared plus xi plus 16 from I equals 1 to I equals 5. So once again, breaking this down. 5 minus 0 over 5, as I previously mentioned, this equals 1 because we have a width of 1. 5 is our right bound, 0 is our left bound, over 5 rectangles, that is a width of 1. Now what we do here is we take our first x value and then just plug it into here, then our second x value, then our third, then our fourth, then our fifth. In our case, for the actual equations, I've used left bounds just because I kind of wanted to. Now what this turns into is this, but you plug in 0, plus this, but you plug in 1, plus this, but you plug in 2, plus this, plus you plug in 3, plus this, plus you plug in 4. All multiplied by the length, which again equals 1. And that gives you our left bound, which is 16 plus 13 plus 6 plus 1 plus 4, which equals 40. And 40 is our answer for the left bound, which, as you can see, I was 1 off of, but close enough. So that is, in essence, what a Riemann sum happens to be.